taking a look at our amino acids, we've seen their generic structure. We've seen their Zwitter ion form and their side chains. One last thing we want to do with them is consider what happens to these amino acids, especially their side chains is what we'll be most interested in down the road, if I change their pH. So let's say I change to pH of 1 or to a pH that's very extreme, maybe of 13, okay? So if it's a pH of 1, this would be taking a protein and putting it in a really acidic environment. Say you spill acid on your skin or you have a protein in your stomach, something like that. So this is acidic, and because it's acidic, there are lots of protons around, right? And so what's going to happen to my amino acids here is they are going to gain H+, or a word that we've used before for that was that we will protonate some aspects of our amino acid. Over here, if it's pH of 13, that tells me that it's very basic, so I don't have H+. This means instead of gaining H+, I'm going to lose those protons, and we had a word for losing protons that was deprotonate. All right, so we're going to consider each amino acid as a whole. I'll do some and then I'll leave some for you to try later. But if I take this amino acid and I dump it into strong acid where I have an abundance of H+, and I went to an extreme, very acidic pH here, then I want to look for anywhere negative that an H could add onto or any amines that I could add it onto. Notice the negative here on the carboxyl group could grab that positive. So if I rewrite this at acidic pH, my amine is already protonated, so I can't protonate that twice. I'm just going to copy carefully here. There's nothing to protonate or deprotonate here. It's all just carbons and hydrogens, so that's going to be exactly the same. And so if I can just keep an eye on where the charges are, when I protonated this amino acid, I ended up adding this H right here, and that was the only thing that changed on it, okay? What if I deprotonate it, so drop this into base? Now the base is gonna steal any extra protons it can, and there's a proton, a positive here, just waiting to be pulled off. So if I deprotonate, then I would end up with H2N, CH. This stays deprotonated now, okay, stays negative, CH, CH3. So the only charge I have now is here. So at a pH of 7, I had both the positive and negative, the Zwitter ion form, but at an acidic pH, now I just have the positive. At a basic pH, I just have the negative. So I'll take a look at one more with you, and then I'll leave the rest for you to do. Looking here at this acid, I've got an acidic side chain, right? So if I drop it into acid, then H's are going to add on anywhere they can, both in the backbone and in the side chain. So when I add those H's on, I keep this amine protonated. Now I'm going to add an H up here, an H here, CH2, CH2, and this becomes COOH. And now it looks more like the acids that we're accustomed to, right? So I just protonated everywhere there was a negative. Now this might seem small, but this protonation of the side chain is going to be enough to disrupt some of our tertiary structures that we see later, and some of the attractions in them. And so protonating this can disrupt how it behaves with all the other things around it. So it's something that we will come back to in a few slides. So you can go ahead and fill in what this would look like at the basic pH, and then you've got two more here to try out in acidic and basic pH.